All right, so we're going to talk about the n-queens problem today. I'm going to give you an example of that and just kind of practice coding through the whole thing. And excuse me for 1 second. Let me close Discord so it stops giving me updates. Maybe the n-queens problem. Just so you can see it, let me sketch this for just a minute so everyone understands what's going on. Okay, so in the n-queens problem, you have a chessboard, and it's an n by n chessboard. And I'll just do one that's 6 by 6 in this case. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so there's a 6 by 6 chessboard. A normal chessboard is 8 by 8, but this theoretically could be any size. And so the idea is, how can you place queens, n-queens on the board? So it's the n-queens problem. And each queen that you have, remember, or hopefully you know chess to a degree, if you have a queen that's here, the queen can cover everything in the same column and the same row and across each of the diagonals. Okay, so the queen can basically attack any of those directions, any of those pieces along the way there. And so the question is, can I place n-queens on the board in such a way that the queens cannot attack each other, that they're all positioned in a way that they can't attack each other? So let me redraw this board and see if we can just do one as a very quick example. In fact, I'll do a very simple one. I'll do a 5 by 5. Okay, so let's say that I put a queen right here. And then maybe I have to put another queen here, because notice this one, and this one, the queen could attack all of those, but can't really attack that one. Maybe I can put another queen here. Okay, so far I've been able to place 3 queens that can't attack each other. Maybe I can do another one here. So I'm doing well. I've got 4 and none of them can quite attack each other. And then the 5th one there. Okay, so I think that worked. I think I did that correctly. So none of those queens can attack each other. So there's an example of a 5 queens solution on a 5 by 5 board. Okay, hopefully that idea at least makes sense to you. And I'm sorry, let me bring up the chat window so I can at least keep an eye on that. Okay, so excuse me for 1 minute as I get this oriented. Still not working. Oh well. Right now I cannot see the chat. I might see it in just a minute. So the idea of n-queens is, how are we actually going to find a way to do this, or maybe find how many ways I can create an n-queen solution? Like, how many ways can I do a 5 by 5 grid? Like, on a 5 by 5 grid, place 5 queens. And so this is a brute force approach. We can basically place queens and check and see if they work. And if they don't, it's not going to work for us. Well, you can think of sort of different levels of brute force. So one of them is, if I've got, in this case, I'll stick with 5 by 5. If I've got a 5 by 5 grid, what if I just place 5 queens at random on there? Queen, 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 queen. Okay, there's 5 queens. And then I check and I say, no, that doesn't work. And I could sort of do every possible combination. Well, in this case, there's 25 spaces on the board and I have to fill 5 of them. So I would have 25 choose 5 over 5, but 25 choose 5. Possible combinations, and that's just too many. What is that? 25 factorial over 20 factorial times 5 factorial. So that's a lot of combinations. I don't want to check that many. And if I got up to a real size chessboard, this would just get ridiculous. So I can't really do that. I can't check every brute force combination. But there are some simple things you can do that will make it easier for us. So what we already know about this problem is, if I have a piece that is in one column, there's only one queen that can be in any one column. And you can think of it as the same thing as a row. So if I set a queen in this column, then I know I never need to put another queen in the first column. So the next queen can go in the second column, and then the next queen can go in the third and the fourth and the fifth. And so I can instead of just placing queens at random throughout the board, I can make sure I place at least one in each column. And that's at least going to save me a lot of options. It's going to keep me from doing something like putting a queen in this one, this one, this one, this one, and this one, okay? Because I'd have 2 here and 3 here and 0 in all of those. So that's going to be our first approach, is how we do that. Now, N queens is an example of a recursive brute force approach. So it's something where we're going to basically place a queen. We're going to check and see if that's okay. If we're still okay, we're going to place another queen. We're going to see if that's okay. And if we get to the point where we're able to place all 5 queens, then, or all N queens, then we're done. And we say, yay, we found a solution. And then we go back. And the fact that we go back and sort of undo our actions and try a queen in the next position is an example of what's called backtracking. It's hard for me to write on this with the orientation it is. So I'm going to run through an example of this just so you can see it, and we'll do a few variations on it. But I want you to see how this will work if we implement some backtracking here. So let's try this. I hope everyone can see the screen at this point. So all right, so I'm going to go ahead and create an N queens problem. And before I forget, by the way, let me try one more time to get the chat window working now that I've switched my view. I do not understand why I cannot see the chat window. It's very weird. There we go. It's just hiding. Okay, and evidently I also need to let people in. Thank you for letting me know that. Participants, admit. There we go. Okay, so I apologize for all of the delay here. Okay, so so back to our what I wanted. Okay, back to our code itself. So so what we're going to do is I'm going to create a board that's going to be of a particular size, and we'll make this a little bit more general in a minute. But for now, I'm just going to define the board size to be 8. Okay, so I'm going to just set N to be 8 so that it's a standard chessboard size, not something that is arbitrary size at the moment. So it's going to be kind of hard coded, and I'm going to create a board that is N by N. And basically this board is going to be filled with things that are, it's going to be true if I have a queen in that position, and it's false otherwise. So it's an N by N board. So if I want to initialize that, I can write something like for int I equals 0, I less than N, I plus plus, for j equals 0, j less than N, j plus plus, board I j equals false. Okay, so we start out with an empty board, and I'm going to create a recursive routine that is going to let me basically see, can I place a queen at a particular position on the board? And if you remember what we said, we're going to place a queen first in the first column, then the second column, then the third column, and so on. Okay, so I'll have a routine, something like place queens. So I will say int place queens, and I'll take in the board that's N by N, and I will take the column that I want to place the next queen in and see if I'm there. So this is going to be C is the column, and this will return the number of ways to get Okay, so this is going to basically tell us how many ways we want to return, how many ways we can place n queens on the board. So our very first thing, in fact, the thing that we want to output is, we'll output something like there are, and then place queens, board, and our first one's going to be in column 0, ways to place queens. Okay, so basically we're going to call place queens. It's going to tell us that there were that many ways to place queens on the board, and maybe I want to say what the board size was. Size. We'll output in. Okay, so pretty straightforward. It's going to make a call to this thing here. Okay, so the first thing that we want to do is this is going to be a recursive function. And so anytime you have a recursive call, the main thing you need is a base case. You always need something to stop. So often the very first thing you should think about when you write your recursive function is, what's my base case going to be? And in this case, if you think of having a board, you're going to place everything column by column across the board until you get to the final column. So when you're in the final, when you've placed your final column, you don't need to do anymore. And so in this case, I can say something like, if the column is equal to n. In other words, if I've already placed 0 to n-1, I've already filled up the board with queens. So if I'm trying to place a queen on a board that's already there, then I say, oh, I've got a complete board. If I get to that point, if I've managed to place all n queens and I haven't stopped yet, then hey, I found a solution, so I'm going to return a 1. That's my base case. Okay. Otherwise, I need to keep track of how many ways there are to place the queens. So I'm going to keep track of something like num ways to place, and set it equal to 0. And at the end, I'll return num ways to place. Okay, so that's the thing I'm going to return. And so now what I want to do is I want to check, I know I'm going to have to place a queen in column C. And then I'm going to need to check and see, is it okay to place it there? I'll check every position in column C. I'll say, is it okay to place it there? And if it is okay, I'll place it, and then I'll try to place one in the next column over and get that. So what I will do is I will have something that I'll say for int I equals 0, is less than n, plus plus. So I'm going to go through all the different rows. So these are going to be the rows. Maybe it's easier to call it R since it's rows. So I'll go through all the different rows from 0 to n. And for each one, I will check and say, like if, and I need something that'll let me know if I can place it. So I'm going to have to create a new routine. I'll call it can place. So if I can place on the board, if I can place row R and column C, if it's okay to place it there, then what I need to do is I will go ahead and I will set that board element to true. It means it was okay to place it there. So I will say board sub R sub C equals true. So I placed a queen there, and now I will add onto the sum. I will say I want to see how many queens I can get then for the next column over. So I will call place queens for board and C plus 1. And then after that, I need to undo whatever I did before. So, okay, so let's make sure we understand what's happening here. In this routine, what's happening? I'm going over this for loop here. I'm going to try every row, and I'm going to try to place a queen in every row of that column. And if it's possible to place it, so I still have to write this routine. I haven't written can place yet. So if it's possible to place a queen in that row, in that column, then I mark that in the board. I say true. I've got a queen there in row R, column C. And then I try to place a queen in column C plus 1. And then after I'm done with that, I remove the queen from there because I'm going to go on to the next row and try it out. Okay, so hopefully that makes sense. And that's actually all I need to do in this routine is place the queens. Now I still have to write this other one. So I'm going to have a function called can place. And this is going to take in a row and a column. Okay. And this is going to either return true if I can, says whether can place row or column C. Okay, so this is going to basically just be my check that says, can I actually place one at that position? So what does it mean to be able to place one at the position? What I need to do is I need to see, do I already have a queen in that same row? Okay, so the first thing I'll do is I'll say, do I already have something in that row? So I'll loop through all of the rows before that. So I equals 1, equals 1, I is less than C, I plus plus. Okay, so I'm going to go through all of the columns up to column C. So I'm going to check all of the previous columns that I've had, and I'm going to say, is there a queen already in that row? So if bool of, or in that column, I'm sorry, if bool of Ri, okay, so I is the column number now. If that is true, then I'm going to return false. In other words, it's not okay to place something there because there's already something in that point. Okay, does that make sense? Okay, hopefully so. I can't see anyone's expression because guess what? We're online. So that's why I like to at least have people in class. I can at least sort of tell if people are getting lost or not, but I can't tell it all here. So I hope you're following it. But okay, so that's going to
Professor Kaiser.
Yeah,
it makes sense. I just wanted to point out right here in the if statement, it's you put bool. It should be board just before I forget.
Thank you very much.
Also, in your main, you use the lowercase n instead of capital N.
Did I really? I sure did. Thank you.
Same with sum as well. You use sum instead of num ways to place.
Yeah, that's because my sample code I wrote out is there. Num ways to place. Awesome. Thank you very much. Everyone's catching stuff. Anything else I've messed up? And this shows you why you should always stop and compile along the way, but I'm just going through. So the question is, why is the base case 1 instead of 0? Okay, good question. So the reason why the base case in place queens is 1 is because if I have placed all the way over and like my columns are 0 to n minus 1. So if I get to where I'm trying to place something in column n, it means I already got all n queens placed because column n is now like too far, right? That's like past the end of the board. And that means that, yes, I found a way to place 8 queens on the board. So that's one example where I made it to a valid case where I was able to place a queen. And so if I do that, like, if there's multiple ways to place queens in this section here, every time I run through, if I find a bunch of different ways to place queens, I can sum those up, and that's going to be the total number of ways that I could place the queens on there. Okay, I could, there's another way you could do it, which is you could keep track of how many queens you've placed so far, but that's what C already is. Okay.
Shouldn't it be C equals n minus 1?
Okay, so n minus 1 means you're in the last column, but you still have to actually place it in the last column. So what I could do is I could say if C is equal to n minus 1, then I just go through and I see, is there a way to place it in the final column? Because if there is, there's only going to be one spot it's allowed. There's not more than one spot. There's only one spot you could possibly place it because every row and every column will just have one. So I could do a special case there, but to me, it's easier to just place it in the last column, just like all the others, and try to place it beyond that. And that's when you say, hey, I made it here, everything's good. And if you go through all the ones in the last column and none of them were okay to place it, you backtrack just like everything else.
That makes sense. Thank you.
Okay. All right, so we've handled up here in this can place, we've done the thing where we've checked to see, is there already a queen in the same row that I'm in? And so we still have to check it and see, is there a queen on the diagonal? Is there a diagonal version of this? And so what we want to do there is, if you think, and I don't want to switch because then I'd have to reopen all of my windows. But if you think of a chessboard, so picture the chess. Maybe I need to do this. If you picture a chessboard in your head, if you go back, if I'm at a cell and I want to say, what are the two diagonal ones? If I go back one column, then I need to go up one row and down one row, right? So if I go back one column, I'm going up one row and down one row. If I go back two columns, I'm supposed to look up two rows and down two rows. And those are the diagonals, right? It's like if I go back X number of columns, then I'm going up X and down X. So what I can do to check the diagonals, let's say I want to check the upper diagonal, is I can say, and I'm going to have to modify this a little bit, so I'll leave some space here. But I can say if the board of R minus I, C minus I, okay, so in other words, if I'm going back, if I'm say one column back or C minus one columns back, however many it is, if I go back by one column, okay, then up one and down one from there would be the diagonal. Okay, so when I is 1, this is R minus 1, C minus 1, that's 1 up on the diagonal. If I go R minus 2, C minus 2, that's 2 back on the diagonal. R minus 3, C minus 3, all the way back until I'm on the bottom row. Now, the reason I said that, or on the first column, the reason I said there's a little bit more to do is you do have to check and make sure you're not going to go out of bounds in your array. So you need to make sure that, what on earth did I do? Don't ask me why I highlighted it. I don't even know what key I just hit. Okay, so I do want to make sure that I haven't gotten so far like back off the top that my row went past the top, right? So if my queen is near the top, I obviously can't go back off the board. So I need to make sure that that R minus I, in other words, the row number is still greater than or equal to 0, and that the board is not. Okay, so that's one diagonal. The other diagonal is going to be very similar to this, except instead of R minus I, it's R plus I. Okay, in other words, I'm going to go back one row or back one column and I go down one more row. I go back one more column, I go down one more row. So each row keeps, as I go back each column, I increase. So these are the two diagonals. And if none of that is true, then I can, if none of those is the case, then it should be okay to place something there. So I can return true, because what that means is I looked on the row, there's no other queen on the row. I looked on the diagonal, all of the diagonal was false. I looked on the other diagonal, all of that diagonal was false. And so since both diagonals and the row were false, it's okay to place the queen there. Okay, so let's try this out and see if this thing works. Nope, I need to add an int down there. Okay, and if I run this thing, I get 0. Well, that's not the right answer, so I've obviously got something wrong here. All right, now it's debugging time. And of course, you should never have a problem like this where you debug something real time, but I'm stuck with it, so let's do that. Okay, anyone know what I did wrong? Did anyone see something wrong? Won't you miss checking if there is a queen in the same row for column? Sorry. Won't you miss checking if there is a queen in the same row for column 0? So oh, that's up here. Yes. And so I need to actually do, this should be C minus I, basically. So if I'm going backward there, thank you. And I bet that's the error.
And shouldn't the that second condition R plus I be less than?
Yep, less than or equal to n, or actually less than n. Yep, very good. Thank you. That's two things. Okay, anything else that anyone's seen? So that was definitely two issues. So let me make sure everyone follows this. So earlier, there was the particular check there where we said I'm looping I to one less than C. So I want to go back 1, 2, 3, 4. So it's like C minus 1, C minus 2, C minus 3, all the way back to 0. And
shouldn't it be I less than or equal to 0?
Equal C. There we go. There we go. Is that better? That now should be correct. Thank you. Y'all have caught everything so far today. C plus.
Why is it not C plus I for the second or for the third if
statement? Yeah, I'm not doing well today, am I? You're right. This is a plus also. No, sorry. This is still minus I. So I'm still working backward on my columns, but one set of rows is going up and one set of rows is going down. Hopefully that makes more sense. So yeah, I think that part's there. Okay, so let's try this out. Okay, there's 92 ways to place queens on the board of size 8. Okay, so that's kind of nice. If I wanted to like check this for 5 queens instead. There's 10 ways to place them on a board of size 5. Okay, that's interesting. Did not know that. Okay, so basically you get this should be, and I hope those numbers are correct. I don't actually remember what they're supposed to be, but that roughly sounds right. This is a way to check through the whole thing. Now, the problem here is, and this is always going to be a problem, if I try to increase this too much, like if I try to make this of size 12, this becomes a little bit problematic. And this might still run fast. Yeah, we still get a pretty good number. Normally, 15 is where things really break down. I'll see how this one does with 14. Okay, yeah, so we get up to 14 and it's just doing a whole lot of recursion. And there's a lot of recursive calls. So in the 13 minutes remaining, there's 2 things I want to try showing. So there it finished doing 14. There's 2 things I want to show you how to do. One is how to make this where I don't hard code stuff. So it's kind of easy to hard code my arrays that way. But we could do the whole thing with vectors. And then I could actually like read in the number that I want along the way, and that will make it more flexible. So I don't have a pound define in there. So okay, so I'll take what I had before, and I'm going to, instead of having this pound define n of 14, I will have an int n, and I'm just going to make it a global variable there to make life easy so that it's easy to change this. And what this will let me do is I can potentially read in a number from input, from standard input. I can go ahead and read in what n is. Now, it's not going to be okay to do this. This should not compile, because I don't think, because the functions can't bring in something. Let's just try it out and make sure I'm not lying to you. The problem is that the function headers are expecting something n by n, and you don't know what n is at the time. Yeah, so it's not going to be able to do that in the function headers. So one way of getting around this is, instead of having something that is a hard-coded array like this of Booleans, we can make this a vector of, actually a vector of bools. And I will initialize it to be of size n once I've read in n. And then instead of just setting things up that way, I can say vector one row and set that if n and initialize it all to false. And then I can, for each one of these, I can go through each row and say, in fact, I don't even need to initialize that. I can just say board.pushback. Okay, so basically I've created a row of length n where everything is false, and then I'm going to create n of those. I'm going to run through in this list down here. I'm actually going to run through the entire set and push all of those back into and make copies of that row in different times. Okay, so now I just need to change my headers here. So it's no longer is a vector.
Is there any issue with always choosing to use vectors instead of arrays?
Arrays can be a little bit more efficient if you know ahead of time how big it's going to be, because it's just a static allocation. And vector, you get copies. Sometimes you really want the copying functions of the vector, and sometimes you don't. And if you do want the copying functions of the vector, then you definitely want to use it. But if you don't, it's a little bit of extra overhead. And so, like, even something like pushback, if you remember how a vector works, it allocates a certain size vector, and then if you get something longer, then it has to copy the old vector, and it allocates twice as much memory. And if you fill that up, it has to copy it and allocate twice as much memory. And so if you think about it, you could have a factor of 2 in terms of how much memory got allocated along the way, and there's like all this extra copying. Again, it's like a constant factor, I think at most 2, that's there, but there is potentially overhead in doing that. Generally, I would say vectors are better to use unless you're trying to like squeeze out every last bit of performance in something. Speaking of performance, it's probably easier to pass things by values, or by reference, so that I'm not doing copies every time into these arrays. So all of this should speed things up a little bit by doing it or that should speed things up a little bit, maybe compensating for the vectors that I have. Is there anything else I need to do? I'm not sure there is, so let's see if there's.
What was your reasoning for switching to vectors?
I can make an arbitrary size that I can read in at runtime. Now you can do that with an array, but I would have had to have allocated the array separately and passed it, and that's actually possible too. But does that make sense?
Yeah, I thought maybe it was for some other reason.
No. Well, that wasn't good. What did I do wrong? Oh, I need to actually. Need to actually include vector. What did I do wrong here?
I think you're missing a semicolon and main.
Oh. There we go. And there we go. And so if I want a board of size 8, I get 92. I can say board of size 5 and I get 10. Okay, so that was all just a way of doing all of that. Okay, so we've only got about 5 minutes. Oh yeah, so Yeah, so there are other ways that you can definitely initialize vectors and stuff faster. You can also initialize arrays faster. There's a lot of things that we can do here. There's one more thing that I wanted to mention, and I'm not sure I'm going to have time to code the whole thing, but I will post some code so that you can see how it works. So I'm going to switch for a minute and just show you one other way to do this. Back on the whiteboard for a minute. Which is the issue with what we had there is that when I'm placing a queen, let's say it's in this row here, maybe in this cell, and I'm wanting to see if that's okay, I'm running through all the previous columns and each of the two diagonals along the way. So remember, those are the three loops I had. I had one that was going back through the different columns, and then one that was going up a diagonal and one that was going down a diagonal. And if I'm doing that every single time, that's a lot of sort of extra overhead because I have to loop through, I have an extra loop and I'm having to check three things in the loop every single time. And there are ways of making this more efficient. And one way of making things more efficient is instead of actually checking each thing in a loop, I can just keep track of my rows and my diagonals and mark, is there something in that row or in that diagonal? So let me draw an 8x8 real quick. I don't know. Hopefully y'all can't hear my wife talking to my dog in the background, although I hear her. Okay, so we are going to keep track of something called rows. And so there's 0 to, in this case, 7. Okay, and each of this is basically just going to be a Boolean array of rows that goes from 0 to 7. So you can imagine just having bool rows of size 7, or I'm sorry, of size 8. Okay, and that's going to just tell you, is there a queen already in that row or not? And so you don't have to actually loop through the row to determine if there's a queen in there. You just identify, yes, there's a queen in that row. Okay, and so anytime I place a new queen, I'm going to not just mark the one cell. So like, let's say I place it right here. I don't just mark this cell in the table or in the board. I also mark it in the rows array. Okay, now in addition to that, we can keep track of the diagonals. And so if we imagine the diagonals, if it's something like this is 0, 1, 2, so this is going to be like 0 here. 1 is going to be this one. 2 is going to be that one. 3 is going to be that one. 4, 5, 6, 7, 8. All right. Actually, what did I do? 7. Maybe I just needed to do 8. Yeah, 8. And then this is 9. 10. 14. Okay, so in this case, the total number of diagonals that you have in that direction is going to be 2n minus 1 diagonals total. Okay, so 0 to 14, so there's 15 in this case. So n is 8, there's 15 different diagonals. And likewise, if I wanted to, I could number all of them the other way. Well, one thing you can notice is the diagonal number here in blue, this diagonal number is just going to be r plus c. And that will tell you exactly which one you have. So if I'm in, row 3, column 4, so 0, 1, 2, 3, 4. So this is column 4, and this is row 3. So if I go there, I should be 3 plus 4 is 7. I'm on diagonal 7. Okay, so that's a quick way of actually checking what row and column you are. And you can do the same thing the other way with the green ones. And I forget which numbering system I've used in the past here, but you can basically identify this one as 0 and 1 and 2 and so on. And again, you do that, and again, you get 2n minus 1 of these. And each of these is going to be something like, let's see, it would be n minus r minus 1 plus c. I think that's right. So this is n minus r minus 1. Yeah. Okay. So n minus 1 minus r is going to like move you up there and over. I believe that's the diagonal that you get that way if you sort of number them all. Okay. So the point is, anytime that I place a queen, I don't have to like do this loop where I check each thing along the way. Instead, I can just have 3 arrays. I can have bool of rows. I can have a bool, diagonal 1, and this is going to be of size, in this case, 15. And I'd have bool diagonal 2, also of size 15. And actually, I should have written this one here is in blue. Okay, and these three things I just update every time I put a queen in. I say, here's my queen. I mark that the row and the diagonals are there. And then if I want to see if something is okay, all I have to do is check my row and the 2 diagonals and see, are all 3 of those false? In other words, do I have nothing there? And if all 3 of them are okay, I mark them all as true, and I can place that queen. I don't have to make a separate call along the way. Okay, so I'll post some code that shows you how to do that more efficiently. I'm sorry we ran out of time for that here today, but hopefully that gives you an idea of how you can do backtracking. So again, kind of big picture here, this is a brute force thing. We're trying to check every possible solution that we can get. And we do that by, we just try the next thing, try the next thing, try the next thing. And if it ever looks like then it doesn't work, then we backtrack and we say, oops, I'm stopping here. I'm stopping my recursion. I'm done. I just go back. And you never keep making recursive calls forward because you check before you place the next queen and go backward from there. Okay, so time's up. I realize people probably need to go. Does anyone have any questions? Oh, wait, question. Isn't it kind of like the depth first search? You check everything and backtrack. Kind of, yes. So we'll get to depth first search a little later on, but yes, it is kind of like that.
How much bigger of an n can you get by doing by not iterating through the diagonals and stuff?
To be honest, not a whole lot bigger, just like 1 or 2 more. I forget exactly what it is. The thing is, it grows exponentially. It's probably not exponentially. Maybe it is. It grows really fast. Like pretty soon, I think beyond 15, you might have to start using longs. Maybe it's 16, and it takes a long time to run. So you can get faster versions, but it's not like, oh, I went from 15 to 30. Doesn't work that well.
That's what I would have thought.